today we're looking at stellar evolution. So, how does our sun compare to other stars in the Milky Way galaxy? You know, the one we're in. And what happens when the sun runs out of fuel or dies? Well, first off, what I need you to do is go into your reference table, page 15. Again, the tool you need, especially for this unit, up at the top right there. I highly suggest use with yours coloring, highlighting, something to show writing and stuff so that it helps you when you go to take the test and whatnot. Okay, this is my bonus to you, that you can use this during your test, which is very, very helpful. All right, so first, find our sun. It's in the group called the what sequence? Well, let's see, where's our sun? Betelgeuse, Polaris, Aldebaran, or sorry, Betelgeuse, Pollux, Sirius, Alpha Centauri. There's our sun, right there. It's in the main sequence, where most of the stars are located. There's a whole crap load of stars right there. To understand the classification system of the stars, you start by looking at the temperature. And the temperature is in degrees Kelvin. Well, what color is our sun? Well, right here I have highlighted with colors, the different colors. You could even go even further, go up the page if you choose to do so. I just colored in the different stars with the different colors. So if I go up, the sun is considered yellow. Oh, sorry. The temperature for this is about, if you look at right here, where there's 4,000, there's 6,000, that's probably 5,000. It's about halfway. So I'm going to say about 55,000 degrees Kelvin, and it's yellow. So I skipped ahead a little bit. Sorry about that. If you look quickly, it's backwards from the way you might think, like the temperature-wise. Because when you think hot, okay, so what you might think. Blue stars are hot, and red stars are cold. Now, this is opposite from what you would see in like a sink or something, where blue is cold, red is hot. Well, here's how you can think of it. If you've ever seen a stove top or a fire, like a gas, not a gas. Is it a gas? Yes, a gas stove top. How they have that coil, if you've ever seen any coils. When they heat up, they first get red, and then they get orange, and then they start to get yellow, and you know it's really, really hot when it's yellow. You don't typically see white. I mean, it could get white. I doubt it, because that's on the very hotter side. And then the blue, white, and the blue, you don't typically see that. You could see those in fires, and if you saw that in a fire, you know the blue flame is wicked hot. You need to stay away from it. Whereas the red flame, not as hot, but still stay away from it. Don't burn yourself. So, all right, so we got the colors down, and this shows right here, this, if I was color in, like right in here, this is kind of how it would look, where you got the dark blue, the blue-white, the yellow, the orange, the red. All right, so there's another thing on here. So down here, we've got color. Now, you look at the luminosity. So what is the luminosity for the sun? Well, look at this. It's right on this dotted line. It is 1. Okay, so that's the luminosity. We're basing everything off of our sun. Sun starts as 1. So luminosity, what the heck is luminosity? Well, that means how bright the star is compared to, and they compare every other star to our star, our sun. Let's stay in the main sequence right here and look at another star called Sirius. So Sirius is right here, which has a temperature of about just before 10,000, so like 9,500 degrees Kelvin. And what color is it? Well, I didn't color it because it is white. And it is about how much times brighter than our sun? Well, let's see. There's the sun. There's that. Maybe 20 times brighter. Yeah. Because there's 10. There's 100. I'm going to say about 20 times. If you switched out Sirius for our sun, it would be a lot hotter. and brighter in our solar system, we probably wouldn't even be here. Like Earth would be fried. Now find Polaris. Polaris is a giant star. So you're going to look in the giants. And is about, well, there's Polaris. If I go down to the best, I'm going to say about 6,000 degrees Kelvin. And the color is yellow. It's in the yellow frame. And is about how many times brighter than our sun? Well, sun's here. Polaris is up there. Oof, I'm going to say like 2,000, 3,000. Yeah, that's a lot brighter than our sun. Now let's look at Betelgeuse. Betelgeuse is a what? So Betelgeuse is up here. It is a supergiant, and it is about temperature-wise, maybe 32, 33, 35 at the max, 35 degrees Kelvin. And what in color? Well, I'm going to say that's red or orange, orange-red. And is about how many times brighter than our sun? Our sun's down here. Let's see. This is 10,000. That's 100,000. 2,000? 3,000? Or 100,000. Sorry, my zeros are off. 100,000 times brighter than our sun. So a lot brighter. Wonder why that is. Maybe because it's bigger. All right. So find 40 Eridani b. It is a dwarf. It is a blank dwarf. So 40 Eridani b right here. It is considered a white dwarf. So we've got main sequence. We've looked at a giant. We've looked at a supergiant. Now we're looking at a white dwarf. And white dwarfs are very small compared to our sun. And it is about, let's see, 10,000, 16, 17, 18,000 degrees Kelvin. And it is a blue-white in color. And it is only blank as bright as our sun. Well, our sun's up here and Eridani b is down here. So it's 0.01 or 1/100th as bright as our sun. So it's not as bright as our sun by a lot. All right. So that's just looking at the characteristics of the stars. You're going to be doing a little bit of work on that in the activity today. So make sure you have your page 15 for your work for today. Okay, so let's look at this evolution that we're going on about. What happens when our sun runs out of fuel and dies? Well, any star, it would depend on the size of that star, what would happen to it. So our sun is a average star. It's right in the middle. And because it's average, I wouldn't say small star, it'll become a red giant. And then a planetary nebula, and then a white dwarf. And finally, a black dwarf. It doesn't have a black dwarf off here, but that's what it would become after. Which is very, very tiny object that emits no light or heat. So it's a dead planet, in other words. If a star is massive or large to start, it will become a giant or supergiant. It could either become either or, but if it's very, very large, it'll be a supergiant. It will become a red supergiant. So massive star to start. So if it was a giant or a supergiant, then it would become a red supergiant, which when it dies, it then becomes a supernova. Like it like goes out. There's a huge explosion which puts out more light than our entire galaxy. It's like lots of light. From there, it will either become a neutron star or a black hole. So what is a stellar nebula? So a stellar nebula is made of dust and gas that form planets or a planet. And then you've got something called a protostar or a planet. It's formed when enough hydrogen fuses together during nuclear fusion. There's that fusion again, due to gravity until it gets hot enough to enter the main sequence. And then next you have the red giants or supergiants. This happens when hydrogen fuel runs out. The planets expand, cool, and change in color. The path that they go on to next depends on the mass of the star. So what would happen with our sun? Well, as it dies, it's going to expand out, and it's going to expand out past the asteroid belt, which means this Earth will be shish kebab and be gone. Bye-bye. which is another reason why we're looking to go off to other planets, is because at one point in time in Earth's history, Earth will have to vacate it. So they're looking to get past it. That's why they're also looking for planetary other planets that are very Earth-like. And there are several. They found several, but it's many light years away, which causes a touch of a different problem because we can't travel there fast enough. We're working on it, though. All right, so planetary nebula. At the end of a giant, a regular giant, the star is unstable and it starts to pulsate. And as it pulsates, it ejects the outer layers of plasma, which is that was the pulsating. It pulsated out and it just pushed it out. And after all those layers drift away, only the core is left, which is typically very, very hot, very, very dense, and that's a white dwarf. And then after the white dwarf, you get the black dwarf. When the thermal energy of that white dwarf cools down as far as it can go, it changes color again and disappears from sight. It becomes a black or brown dwarf because you can't see it anymore. No more energy coming off of it. Now, if we were going to the supergiants, the large ones gets to the red supergiant, what happens next? Well, a supernova. What's a supernova? Supernova is the explosion that occurs when the star runs out of nuclear fuel. So it has no more fuel and it just like explodes. And it puts out more light than our entire galaxy. And it could either go one of two ways after it does that. It can go to a neutron star, and this also depends on like the size. The bigger they are, the more they go to the black hole. On the smaller end of that, they go to a neutron star. So it's an incredibly compact core left behind after a supernova occurs. That's why I said it's on the smaller side of the supergiants. So it condenses down to an incredibly compact core left behind. And then a black hole that's like huge, very, very massive, generates 4 times the mass of our sun. So it's the remains of a star crushed into an incredibly dense object. Like the density is off the charts. So it starts sucking in because the gravity is so strong, nothing can get away. All right, so that is it for the notes for today. Make sure you do the activity. Use your reference table. Hop on Zoom if you need help. I'm here. Don't forget, once a week with me. Besides that, you guys have a great day.